this talk is about Orbifold fundamental groups for Calabi-Yau pairs. So basically, this talk is just a spin-off on the idea that, when you have some positive or zero curvature for, some algebraic variety or some pair, or locally for some singularity, your fundamental is too big. Probably no free group in it. And probably maybe finite if you're lucky, maybe virtually abelian, maybe virtually nilpotent, maybe virtually solvable. So there are lots of statements along those lines, and this is about the statement in this way in dimension 2. So I'll spend some time motivating everything, and the talk has a second part in the title that's in the group the Cremona group of the plane, BRP2. So those are the two parts, and I'm going to spend some time explaining which fundamental group I'm looking at and some historical motivation and so on. So for you to not get bored, I meant to give the BRP2 part now, and then it's just as a little snippet, and then start to talk about fundamental groups, and at the end connect the two together. So this whole little it won't be the connection yet, but there's a theorem by okay, so maybe let's start with an example. So you all know A5, which is probably the simplest simple group, which has size 60 and is the alternate group of size 5. Well, it has a phase-pool representation in PGL2C, which means it has a phase-pool action on P1 of C. And that's great, because if you take it twice and take a semi-direct product with Z to Z, well, that's going to be acting on P1 times P1, just by acting on each factor, and the involution flips the two. And that's a pretty big group. So it's finite, but it's still of order 7,200. And that's pretty good, because you could tell me on P1 times P1, you can make infinite group acts or very large group acts, just from the toric structure. Just had some very big cyclic group act on each side. But this one is somehow even crazier because it doesn't have any normal abelian subgroup or normal nilpotent subgroup or nothing, right? So it's not simple itself, but it's very you can't. So it's it has no normal, say abelian or cyclic or whatever you like subgroup. And there's a theorem by, so I'll put Jasinski, his name, I think 2019 probably, or 2017. 2019 indeed, that for every G that acts, that's a subgroup of the Cremona group, P2C. You can find a normal subgroup in G that's abelian and has index at most this number. And so in a way, this one is the worst one that can happen here. This type of property is actually shared by other groups in this. So it was first, I think, witnessed in groups like GL and C. And it's quite remarkable that it happens in such Cremona groups, and it's called a Jordan property. Here we won't use, so it's just this phenomenon where you have an explicit bound where any finite subgroup in a group has, is virtually abelian with a prescribed uniform index. So this is a Jordan property. And all GLNs have some, so GL2 has Jordan constant 60, for instance, and you can, care about those things. And so one of the main points I want to explain today is that this is going to connect with studying some fundamental groups. And I'll write a theorem, which will be the main theorem today. So the paper isn't on the archive yet. We hope to put it there in a week or two, but it's been a month or two that we've been hoping that, so we'll see. But then I'll write the main theorem, and then I'll move on to define everything that's in the main theorem, but just so you see why I'm talking to you about this. So the main theorem is X delta be a pair, or mx equals 2. And it has, you want it to have log canonical singularities. Again, don't worry, I'll explain. And with kx plus delta, which actually will just be a Q-Weil divisor. We'll talk about that later. Okay, then there's a notion of regional or orbifold, people give it different names, fundamental group, which again I'll define in a second. And so it has a normal subgroup of index at most, again, 7,200. That is, yeah, and so what's this normal subgroup? Well, when we first wanted to prove it, we hoped it would be abelian again, but that turns out to not be true. That is, so there are two cases. It's either abelian of rank at most for it, or that is a quotient. So basically, either it's abelian of rank at most for, or it's, you know, not abelian but still nilpotent. But if it's a nilpotent, it's quite explicit what it is. So it's going to be a group that looks like the Heisenberg group, like the discrete one. So you have 3 generators, and the first one commutes with the 2 others. But the last 2, the commutator is the power of the first one. So, you know, one way to think of it is it's a group that has Z inside and a Z2 as a quotient, and this map doesn't have a section because, you know, the B and C, they come from the Z2, but you can't get the whole Z2 back in there because they don't commute up there. All right, so that's the theorem. And so as you see, the notions, so of course I want to give a lot of motivation for this, but the notions, the main things are, okay, dimension 2, we just really can't get rid of it, and we'll be running a lot of MMPs and whatnot, so, you know, dimension 2 is a nice case where everything works well, and we have, you know, minimal models and so on. Like canonical singularities, you should be, I'll explain, but you should be thinking of it as a local condition of zero curvature. So, you know, it's like you get singularities, and near the singular points, nothing's too bad. So it's a little more, so you could think of it as a limit, but here, it's a little more general of this KLT notion that appeared in Professor Fujino's talk and in this Braun theorem. And I'll talk about the Braun result notes in a bit too. And this is a, you know, so this is like a local, you know, positive or zero curvature condition. And this is just your well-trusted, like, global. Okay, zero curvature, I'll put positive or zero curvature condition, just because it's easy to put some Fano style thing in this framework. Okay? And then maybe last but not least, what's this fundamental group? So the first main point I want to say is that, you know, the usual fundamental groups parameterizes some étale covers. And so, you know, you have the usual fundamental group just parameterizing any étale covers, and then you could do this étale fundamental group that parameterizes covers that are algebraic, and that's like a profinite completion. And so here what we do is we have a spin-off where we don't parameterize étale covers anymore. We parameterize covers with allowed ramification. First of all, above the eventual singular points of X. Second of all, above the components of delta, but with some bounded multiplicity given in the coefficients of delta. So I'll make this precise in a second. And then again, you know, if you try to parameterize some ramified covers, you could try to only parameterize, you know, the algebraic ones and get some étale fundamental group that's maybe smaller. Or you could do what we do in this paper, which is just get a good old, you know, topological pi1 that maybe has some crazy infinite things that aren't witnessed by algebraic covers. So here, yeah.
Can you recover the theorem of Jasinski using U?
We use it, so we use it, yeah. We could possibly not use it, but okay, maybe this is a good point to explain this. The good thing with the theorem of Jasinski that will appear, we'll use it a lot in the proof, because somehow, it's hard to build. So we could prove without this bounded index, the theorem, without using Jasinski's result. Now the hard thing is, as I told you, you were studying, some finite covers, ramified, that are actually Galois covers. And to get a normal subgroup, we have a Galois correspondence, so those normal subgroups of finite index will correspond to finite Galois covers. And the problem is, if you want an explicit normal subgroup of bounded index, we need to actually very much, see, we start taking a first cover, and then maybe it's not good enough, so we take another one. But then the composition of Galois thing, maybe it's not Galois, so, normal and normal is maybe not normal. And so the thing with Jasinski result is we just, take lots of covers without paying attention to the degree or the index, and then at the end, a posteriori, we bound the index using his result.
Where this last group comes from? Some elliptic?
Yes, I'll explain. Yeah. I'll explain. So basically, the thing is, I want to motivate this, and for those who are bored, try to come up with an example where this group shows up. So this is optimal. This happens too, and I'll explain why a little bit later. So now let me just maybe give at least a definition of this and some motivation why we should study it. So, not in green. Definition. So we'll start with a pair. So X is just going to be some normal projective variety over C, and delta is going to be some very explicit sum of components, and the data are, like irreducible, reduced, veil, effective veil divisors. So if you're a surface, just think of them like they're curves, possibly not normal. And the AI, what's important is want them to be between 0 and 1. And allowing 1 is kind of a main change in this talk, because people have done a lot of things about KLT, but KLT means you don't allow 1, you just allow smaller things. But today we allow 1. Okay? So that's what we'll call a pair, and we want, okay, so we'll want X to also be Q factorial, just so we have, Cartier divisors showing up. And we want also coefficients in Q here, and we want Kx plus delta to be in Cartier. So that's pretty standard, I think, as assumptions for a pair. Another question is, how do we define pi 1 reg of x delta? So it's going to be, you take, x, you remove the singular points, and you remove the whole support of delta, and then you take the pi 1. But of course, you threw out a lot of things, and it's kind of crazy that if there were like tiny AIs, you threw out the D1. So now you mod out by some normal subgroup. So for each delta I, you can consider a small loop in a tabular neighborhood around it. So gamma I will be a small loop around di. And basically, you prescribe it to be torsion of a certain order, and that order is given by the AI. And so, gamma, oh yes, exactly, thanks. And so you had, okay, so you're gonna quotient by this, and here you're gonna need to normalize. So now that I've written all of this, let me just explain. So basically, for all data, you take a little loop around it. But if data appeared with coefficient 1, and you have a 1 here, you can't put 1 between two numbers of this type. So if you have a delta 1, for instance, that appears with coefficient 1, you just don't put any loop. So you just remove it and don't do anything more. And now if you have a delta I that appear with a coefficient of this form, then you want to branch, then you want the loop around it to be n torsion. And when you have coefficients in between, you just round down and then ask for torsion. And in particular, if you have a lot of elements, a lot of components that have with coefficients strictly smaller than 1/2, you just completely forget about them. And the motivation for this So this is called the standard approximation. So it's just a way of rounding down reals between 0 and 1 to numbers of this form. And we'll use it a lot. And so basically you just quotient by this and you want to normalize because, you know, taking those tiny loops, we have completely been forgetting about base points and things like this. And so gamma is not really defined in itself, well defined, but, you know, up to conjugation it is. Right?
Is there a particular reason why you don't start immediately with standard coefficient?
Yes, that's a good question, because basically we want to encompass way more stuff like this. Because for instance, if you care about, you know, Fano pairs, like toric pairs, things like this, then you're going to start with X delta, that, you know, is with like ample anticanonical. Then you can always complete it to get a pair like this, just adding, you know, tiny things with like general components. And so this will encompass, you know, some Fano pairs, but with non-standard coefficients. So a good example, yeah, so I was going to give some examples. So, you know, you can just start trying to compute it. So sometimes I don't put the reg as an uppercase, it's just when I already have an X that moves, because reg I just mean, you know, take the regular locus. So examples. So, you know, the most basic example is maybe just 2 points in P1, you know. Then, you know, you can just look at your group and it's just like you have two generators, one is the inverse of the other, one is order n, the other is order m. So this group is just C, and you take the greatest common divisor of n and m. And so you see, for instance, this one's already an example for you. Cis pairs wouldn't be encompassed in the theorem if we had said, you know, if you put, I don't know, n's at least 5 and m's at least 5, or, you know, if you take n and m big enough, this gives you a pair with standard coefficients that can't be, you know, made into a bigger, you know, into Calabi-Yau pair with standard coefficients. And so somehow if you want to, the theorem to have some Fano cases too, you allow non-standard coefficients, just because if you have something Fano standard, you increase a little bit to make it not standard anymore. And it also allows you possibly to encompass some, you know, non-Fano, kind of neither Fano nor Calabi-Yau thing, where you're like P1 times E, so the anticanonical is, you know, not ample but nef and so on. Okay, so that's a basic example. There's another one that's actually quite funny. Like this one. So this one, you know, you have two generators that are involutions, and then you know, you'll just get their inverse. So, you know, it looks like, oh, we already found a free group or something, but, you know, they're just involutions. So it turns out it's a dihedral group. So you take AB, like the product, and there generates a cyclic group, and that's the group you get. So again, you know, some non-finite group, but still, you know, something virtually abelian. And then there are two more that I want to do, but basically they're not necessarily so easy to do from a group theoretic point of view. So, you know, I'll maybe write a proposition before explaining how to compute them. And 6 7s. Okay, maybe let's do 5 6 as well, and 6 7s, and then we're happy. And why do we care about this free example? Because, you know, this one is Fano. If you sum, you get like something smaller than 2. This one is Calabi-Yau, because the sum is exactly 2, and this one is the first kind of general type example. And so, you know, how do we compute those three? Well, if you like group theory and, you know, trying to figure out a group from its presentation, you can try to do it, but, you know, it's not always easy if I give you just some finitely presented group to figure out what the group is. So let me maybe write a proposition, which I think was known to be true and kind of folklore by a lot of people, but I couldn't find a proof anywhere, so we wrote a proof in the paper. So it's like, so you take a morphism between two pairs. Sorry. Let's go like this. So just x prime to x, finite Galois cover. And you want x prime delta prime and x delta to be pairs, just as So so basically to have a map, we just want to say, when you have usual fundamental groups, as soon as you have a map, you get the push forward. And we want to say, no, when we have like push forwards for map of pairs. And so the point is, a reason to have it, we need some kind of compatibility between delta prime and delta. So what we want is that pulling back delta, we really get delta prime plus the ramification. And that's really good also because it means the canonical of the sphere when pulled back is exactly the canonical of the sphere, and it also gives you kind of singularity compatibility here. But it's not enough because it's not going to give you something nice when you standard coefficients, because here maybe if you have ramification, you take some coefficient, you multiply it by something big. And of course if you multiply something non-standard and then you standardize, it's not the same as if you standardize and then multiply. And so you want another condition that, also for the standardization that's the same. So this I might call it before E-compatible, like it's compatible finite Galois cover. Well, then you have a push forward map, and it's injective, and it sends the fundamental group of this pair to a normal subgroup in here of finite index. So then there exists a push forward like this. Okay. Even better actually. So you have a push forward like this, and the quotient is just the Galois group of your cover. So you get something exact. And I won't write it here, but actually if you have, several like finite Galois covers and the composition is still Galois cover, then you get that the push forward is functorial. So you can compose and then push forward, or you can compose the push forwards and you get the same group homomorphism. So this is all very nice. All right, and so now let's just go back to these three groups. Well, this basically tells you that if you manage to realize this thing as the branch locus, if you manage to find some curve with a group action and take the quotient is P1 with, these as the branch points of your cover, then the Galois group, like the group by which you quotient is exactly this fundamental group. And so basically the thing is here you have 2, 3, 5, so your group should have probably an order that's divisible by 2, 3, and 5, and the right kind of stabilizers. Well, it turns out it will be just A5 for this one. What about this one? Well, you want to do a cover that covers degree 1/2 here, 2 branches in those degrees at those points. So one thing you can do is you take a degree 3 cover that branches at those 2 points, and so then you're going to get 1 point of degree 2, 3 points of degree 1/2 and 1 point of degree 2 up to this 3 to 1 cover. And so you have 4 points of degree 2. So now you have 4 points of degree 2 in P1. You branch at those 4 and you get an elliptic curve. And so basically here you're going to get the z squared, that's the P1 of the elliptic curve, semi-direct z6z. And if you want to really see what extension you have, just see this as z brackets, 6th root of unit, and this one acts by multiplication. So this is very explicit. And now which is this one? Well, this one you can imagine if you try to do a cover that branches in this way, you're probably going to get a curve, a hyperbolic curve. And turn out you're right. And so basically what you're going to do is you have a cover of degree 168 and of Galois group PSL2, 7. So it's also a simple group that it's going to subject onto. And the kernel of this is going to be P1 of a curve of genus 3. So, you have 6 generators and the product of commutator is the same. And why is this example kind of cool? Well, okay, so the first example where you really get a free group in there. And the other interesting thing is, if you look at this curve, it has genus 3 and it has a quotient with Galois group this. So this Galois group is acting on this curve. And, 168 is like 84 times 3 minus 1. So it's a Hurwitz curve. And so, this is the Klein-Kordek. And basically, if you want to try to build more Hurwitz curves, you kind of can do it the same. You look at P1 and you'll take like some generators and you want to find, some group like here. So basically here you get the surjection from, saying this group can be generated over two generators, one of square trivial, one of cube trivial, and their product is of order 7. And PSL27 is such a group. And so basically from such groups and from such surjections, you get covers from this proposition, and you can build a lot of Hurwitz curves in this way. So that's pretty cool. And that's, that alone is a good motivation, I think, to study Orbifold covers. All right.
The compatibility, you need both the condition or just the second is enough to have the exactness?
I need both for compatible. So basically, no, the second is enough to get a push forward, but I also want this one because basically I want, if this pair is KLT, I want this pair to be KLT2 or LC-LC. I want it to stay Calabi-Yau and whatnot. Okay. So I just put both, but yeah. And I mean, most of the time I'll start with a curve, with a pair, and I'll try to cover it. And so I'll just start off with a delta, and so I'll build my delta prime to just make it work. And for that, I just have to check that ramification is all right. And if you start with delta standard coefficients, which will be the case quite often, then they're the same. So yeah, but second one would be good enough. Okay. Okay, so that's probably enough. And now maybe let's move on to surfaces and also a little bit of motivation. I didn't define. I have until like still half an hour, right? Okay. Yeah, so let's do a little bit of historic, like a little bit. So the question, and the main theorem is this curvature positive versus P1, tamed. Okay, so I mean, possibly the first thing is X of smooth Fano. Then P1 of X is trivial, and if you remove Fano and put rationally connected, then it's also true. Plus something people already knew for a long time. And then you can go to the other critical case, which is trivial curvature. And in this case, maybe I'll attribute it as a corollary of this Bogomolov decomposition. If you have such an X, you can get some finite étale cover, and then X splits as abelian and some simply connected things. So phi 1 of X is virtually abelian, and the rank is at most 2 times the dimension, and the index. So the index isn't bound in the usual Bogomolov theorem, but you can get this decomposition to be Galois, and then to bound the index, it's like asking how can you make finite groups act on K, K trivial stuff. So index bounded, say, and then 2 is reasonable, and then 3 I'm not sure if it's done because you'd have to bound like 3 actions on Calabi-Yau threefold, and that's kind of hard. So I was thinking about it, but it's a fun example, take a Calabi-Yau threefold, what's the biggest, simple group, or at least symmetric group you can have it act on. So this involves questions about free group actions, which are actually not easy to construct. And if you're interested, you can ask some questions. There are some references, like this paper by Ogiso and Sakurai from the 2000s, and some more recent people working on it, at least in the abelian parity case, but let's move on for now. And now you can, and then people just realize, with the minimal model program, if you care about these type of varieties because they're minimal models, well, you better be ready to deal with them when they're singular too, because when you run an MMP, you get singular varieties. So, KLT settings at the very minimal. And then people, I think, conjectured for a long time, but didn't know yet, until this paper by Braun. I'm sorry for the dates, I think it's up to 1 or 2 years old, papers that are both preprints and published. So I'm going to date everything to 2019, but maybe it's incorrect. No, I'm trying, but Please correct me if you know the date or if it's your paper, because I'm going to also cite things from people here, so feel free to give me the right date. So X SKLT. So actually the Braun paper is really cool because it does it in a lot of cases. So you take, for instance, X delta KLT here. That's weak Fano, so minus kx plus delta is big enough. If you don't like big enough, just take ample, that's fine too. Then pi1 reg x delta is finite. And there's also a local version where you take a local group at a KLT point, and that's still finite. So that's really great, and I think people were super happy with this result. It's really cool. We actually use it in the proof of our main theorem, so he deserves a lot of credit for that. But then you want to move on, because the story of, this is great, but this is not enough. Because, then what happens when you start throwing in, a little bit of zero curvature? And now comes the fun, I guess. And so now basically we just want to, let's stay with KLT, because it's the usual singularities you get from the minimal model program, so why not? But, let's replace weak Fano by Calabi-Yau and let's see what happens. I hope this is dry enough. All right, and so here the fun begins, because in dimension, we still have the Bovil-Bogos. Okay, so number 4 is, what about, let's not even have a divisor, so let's just have xklt, kx non-trivial. So what do? Well, due to rather recent and very cool papers by a lot of people, Graf, Guénancia, Québecus for one of them, Stéphane Druel, who's here, my advisor, who also was a very nice person and is a very nice person, and Pétanel, and this is genuinely 19 for this paper. Stéphane, I don't know, maybe 18? Yeah, great, then it's perfect. So you still have a singular Bovil-Bogomolov decomposition. So, of course, there's a price to pay. So instead of a finite étale cover, you have a finite quasi-étale cover of X. So you have a finite quasi-étale. You can ask Galois if you want. You're not losing much doing that. By X tilde, and X tilde is going to be, again, a product with abelian varieties. And now singular Calabi-Yau and hyperkähler thing. Or maybe EHS is a better word in this case. But now the price to pay is, how do you define EHS and Calabi-Yau in the singular case? And well, the definition is very unfortunate because you might know the definition of Calabi-Yau as, well, the H10 is always 0 except in the extreme degrees and the group fundamental is trivial. But the problem here is that we can't just ask for the fundamental group to be trivial. And so the definition is H0y is always 0 except in the extreme degrees, not just for Z, but for all of its quasi-étale covers. And we have no idea, if Z actually has no quasi-étale covers, or if it has a bunch and we have to check it on every single one. And so in practice, I can give you, some very dumb things like hypersurfaces and weight in projective planes, spaces, and tell you, is this a singular Calabi-Yau or not? And you'd say, well, it's anti-canonical in Fano, so it should be Calabi-Yau, but then it's actually not so easy to prove, because you have to check, the covers and whatnot. So problem. The P1 of a singular EHS or Calabi-Yau, or even of the regular locus, or both above, reg locus of them. No idea what it is, and it's not simply connected by definition. And so then, this paper is very nice because I give a lot of examples of what we know and what we don't about this. So the good news is that the dimension is even, then these, so plus even dimension, then the pi 1 is finite. And the pi 1 rect, if you take the profinite completion, is finite again. But if you don't do the completion, maybe it's infinite, we don't know. And now the problem is, what about, so let's, read upwards. What about odd dimension? And I'm not just saying in the abstract, I'm just saying, dimension 3. So you won't have EHS, but take Calabi-Yau of dimension 3, what's its pi 1, what's its, pi 1 of its regular locus? Well, people don't know. Could be finite, could be infinite. The best we know, I think, so far is that if you take any representation of finite dimension over any field of a pi 1 of the Calabi-Yau threefold, the image is going to be finite. But we also know something crazy, that if the group turns out infinite, then it does not have weakly polynomial growth in the Gromov sense. And weakly polynomial growth has a vibe like your group is virtually nilpotent. So somehow we very much hope it's finite, but we don't know. And there's evidence that if it turns out not finite, then it's probably a very weird group. So, maybe question. And I think, I don't know, I for because Braun's thinking about it, and I hope he solves it because it would be great, and it would make for an even nicer decomposition theorem. So the question is like X, Calabi-Yau threefold, even with canonical singularities if you want. There's, P1 of X, P1 of X reg. Even if you do it with some profinite completions, would be happy. Finite. And that's not known. And yeah, so that's kind of the end of what I wanted. No, that's not the end of what I wanted to mention. Last thing for the Calabi-Yau case, for the KLT case, for the Braun result, is here you see it's finite. And Mirko was asking earlier, do you have a uniform bound, in the dimension? Like, is this just, I don't know, in dimension 2, would you just have, this is always 7,000 something or whatever? Well, the answer is no. And again, for the same reason, you could just have some very big cyclic group acting. And so there's a paper by Braun and Fano and Moraga and Roberto study from, I think, 2019 that says that Braun's finiteness is, okay, this is a terrible way of saying it, so okay, so X delta, so I think they do it for local fundamental groups, so KLT with Fano. Then, so dimension n, so there exists a constant C of n, such that for all such pair, pi 1 of this pi 1, which Lucas Braun proved is finite, has, a billion normal subgroup of index at most Cn. So basically the upshot of this is that Braun proves finiteness, but finiteness is not uniformly bounded, but this, virtually abelianity is bounded in this finite group. So it's like a Jordan type property again. So I have 3 minutes, I guess. 15, that's great, okay. I was gonna try to do the proof in 3 minutes, but if I have 15, then it's wonderful. Then I have time for even one more, 4, 5, 6. And so number 6 is that, okay, well, this doesn't work in dimension 3, and we have, the smooth case, but in singular dimension 2, then it's also done. So if you take x, so I think this is genuinely about x delta. So you take x delta KLT Calabi-Yau here, the next 2. Then there's a paper by Campana and Claudon from, I think, 2014 that says that pi1 reg of x delta is virtually abelian. Great. With no explicit bound though, but this is already pretty great. The paper is actually about a lot of other things like fundamental groups of special varieties. They call it almost abelian, but what they mean is really virtually abelian. But it's also a very good paper with interesting ideas. But yeah, so basically, when we started this paper, I think we set out with this Braun result, this effectiveness in this thing in dimension 2. And there was a third thing, or I guess a seventh thing, depending on how you count, that is a preprint by a student of Moraga, Fano and Moraga, from 2023. That's about, LC singularities. If you look at local fundamental groups, so you take x delta x, and you look at this one. And so, as we said, the LC singularity is what one should expect, that you're going to get probably much crazier stuff than in the KLT case. And what they prove, so they only look at them in small dimension 2, 3, 4. But what they say is in dimension 2, so if x has dimension 2, this is an LC singularity, then this group is virtually solvable of length at most 2. And the normal subgroup from the virtuality is index at most x. And so here I have to credit Gabby, who asked me, okay, I was telling him about this main theorem, and he was, yeah, we prove it's virtually solvable, blah, blah, blah. And he told me, is it nilpotent or not? Because apparently people care a lot about solvable non-nilpotent fundamental groups. It's hard to build examples. So I kind of looked, actually today, prepping my talk, when what they prove, these local groups, they're virtually solvable, wouldn't they be virtually nilpotent? And so I took some of them, and you play with the presentation and try to find some exact sequences and build your group in a different way. And I think, I didn't check all of them yet, but most of, it looks like they're probably all virtually nilpotent, and you just have to increase the index a little bit, like maybe 60 and not 6 or so. So probably, sorry Gabby, no examples that are solvable non-nilpotent, not today. Dimension 3. So basically the paper has some partial results, like this is not going to be a free group, but it's mostly no idea. They also, in this case, they also actually really classify, which presentations of group that you can have. The worst one is like 4 generators and 7 relations. So that's the one I checked to see, and this one is virtually nilpotent, then you have other ones on like 3 or 4 generators, so it's not crazy. And then dimension 4 and more. At least dimension 4, well, this can be a free group. At least on 2 generators, possibly even more. So big. Okay, so you see, dimension 3 is really the hard case from this point of view and that point of view, but dimension 2, maybe we can do something, And so that's where we started for the theorem. And now we have maybe not 15 minutes exactly anymore, definitely not once I've erased, but I still have some time to convince you.
Can Fano and Claudon describe also when the fundamental group is actually finite in the KLT case?
I'm not sure. So yes. Probably just when you don't have a torus, okay, this is maybe some a posteriori knowledge, but once you know it's virtually abelian, you just, you take the normal finite index subgroup, you do your Galois trick to get this cover that you want.
I agree.
The abelian groups actually even finitely generated, so remove everything torsion, doing your cover. I can't erase and answer your question at the same time, so let's erase. And so you get this cover, and then you wind up with something that really has, z or z squared as its fundamental, or up to z to the 4 as its fundamental group. It's really just the power of z. And then it actually means your thing is already like Gorenstein. Like you already have that kx is already Cartier. Otherwise you have an index cover and you have some torsion elements. And you wind up using, you wind up with something canonical, like a surface with canonical singularities that's Graf and Calabi-Yau, and it's probably just going to be a very. Oh, thank you. Yeah, I shouldn't try to talk about it. I'm sorry. Right. So now we have a theorem. How do we prove it? And so at least the most important thing is I want to explain to you why this Jordan phenomenon with the BRP2 shows up. And the other thing is, we're at the birational workshop, so I also want to tell you why all of this is birational. So basically we start with sketch of proof. So basically the idea is we're going to run an MMP. So we start with our X delta LC Calabi-Yau pair of dimension 2. The first thing we can do is just, blow up enough things to get a DLT modification. Because LC singularities can be very, very bad. But you can always blow up if you really want everything to be nice, blow up enough to have a log resolution. But we don't need that. At least get, DLT modification. So that's the whole thing, and that's what makes the result a little technical, is that between LC and KLT there's a lot of wiggle room. And that's because, in LC we allow coefficient ones, but we also allow things with coefficients smaller than 1 to intersect themselves a lot, like very bad, like some very bizarre, lots of branches being at the same place. DLT is better, because basically DLT is we still allow some coefficients once, but in terms of singularity, the only thing we allow is either KLT points or, normal crossings. So it's not as bad. And also the good thing is if this pair is DLT, then X prime itself is a KLT surface. And so that's very good. Once we have this, we run a KX prime MMP. Okay, so I'm sorry, so I didn't say that, but the PA1, this regional fundamental group from here to here doesn't change. Because what you're blowing up is, contained already in locus you had removed. So here nothing changes with the PA1. Then you do some MMP, and when you do some MMP, so you're going to be contracting a lot of stuff. But the thing is, the group you get at the end surjects in the group you had at first. And so, if you prove this is virtually like what abelian or nidpotent, blah, 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 then you're done. And so here you wind up with a, minimal model x0 delta 0 set. And now, if you wind up, in the NEF case, and kx0 is NEF, but it's also anti-effective, so kx0 is non-trivial. And so in this case, you're basically in the Campana-Claudon case with delta equals 0. I'm sorry, I forgot to say, in that case, they actually only do standard coefficients. But here, we don't have divisors, so of course we have standard coefficients. So this is Campana-Claudon, so basically we just need to prove an effective version of their theorem. And the theorem is actually effective with index 3840. So, you just look at actions of K3 surfaces to get this. So some kind of effective Campana-Claudon does it. Then you have the Mori fiber space, and then you have the, Fano of the power rank 1 case. Okay, so basically the bad news, though I have to warn you, is that when you run this MMP, since it's a KX prime MMP, you might contract stuff that, you made everything nice and DLT, but you start contracting stuff that you had blown up here. So X0 is still KLT, but the pair, maybe it's LC again, maybe it's not DLT anymore. And so, maybe we are not happy and we'll need to take some DLT modifications of this one and run some MMPs somewhere. But, here we don't care about delta 0, so here we can just do it even under this. So this pair, that's just LC, here we don't care. And the Mori fiber space cases, we have some Mori fiber space on curve, because here, of course, it's the Mori fiber space on a point. So here we have a very nice thing, that we have x0 delta 0, that maps onto a curve, and we can apply some canonical bundle formula, since this is a Calabi-Yau pair.
I don't understand how we can achieve this x0 with trivial canonical bundle.
So what I'm saying is I run an
Because
MMP.
originally the X could be something closer to Fano, for example, no?
Yeah, I mean, it could be, so that it could be like this to start with. The main case where this happens is if you start with this X already with no divisor, or maybe you started with a divisor, but then you contracted all of that through MMP onto singular KLT points. But this is pretty rare. Yeah, it doesn't happen. But you have to take care of it because in itself it's a case that's in the theorem, right? But yeah, this is not the most important.
It's zero, it's just us in that case, right?
Yeah.
Yeah, so nothing has happened.
Yeah, in this case nothing has happened. In this too something has happened. Yeah. So in this case you get you can run canonical bundle formula. So on the base you have actually your curve here is already going to be P1 or an elliptic curve. And the other good thing is since you're a Mori fiber space, the fibers are reducible. But things are singular, so you can have some multiple fibers that make it fail to be smooth. And you could also have delta zero could have some vertical components. And so the good thing is you can put a divisor delta C on C that's almost like the discriminant, but it basically only accounts for multiple fibers and for vertical components of delta zero. So it's like smaller than the B you get from the canonical bundle formula. But they're not always the same. They're like this. And so the good thing is C delta C. Delta C will have standard coefficients, and this is going to be a pair that's Fano or Calabi-Yau. And again with coefficients smaller than 1, so still LC. And the thing is, for pairs it's very easy to look at all the possible fundamental groups. So we did for a lot of P1 with some points on them. We did almost all of them. But on elliptic curves, you can't have anything. So this is pretty classified, what can happen on the base. And then you have the fiber F, and you can restrict your divisor to the fiber and see what it is. And again, you get a pair. That in this case is Calabi-Yau. And the good thing, so MFS continued, is there's a Norrie trick. So it's in a paper by Norrie, and then people wrote a lot of kind of extensions of it, that actually you have an exact sequence where you take the pair you got of the fiber, the pair, so from now on, I'm going to call this X delta, just to not put zeros everywhere. And then you've got the pair downstairs, and then it's surjective. And so this is really good, because now, in a lot of cases, this and this are quite easy to know, because it's classified, there are finitely many options, and then you have to figure this one out. And so basically the thing is now you need to distinguish some cases, and so the harder case is when when either C is an elliptic curve, or when C is a P1, but this parametrizes, finite cover that's an elliptic curve, so it's like elliptic type. So if this is elliptic type, then this group is like it has some Z2 in it. So up to some finite cover on the base and some base change, you get think of this as Z2. On the bright side though, if you have an elliptic curve, if you try to continue the sequence with higher homotopy groups, if this is an elliptic curve, it's like S1 times S1, where the P2 is trivial. So in the base of elliptic type case, you get something, injective here. And so now, you have a Z2 here. And so basically here you can see, what happens. And most of the time, so if you have a Z22, it's going to turn out like, basically you already thought it was something Calabi-Yau with standard coefficients. And so that's going to be pretty good. If here you have something with just a Z, so you could have Z or dihedral group like this infinite, then it means that this is probably going to be P1 with either 1/2 like we had before, or with just 2 points with coefficient 1. That's the very bad case with the HK. And then the last case is you have the sporadic type ones with like A5, you can have S4, things like this. And then you have a finite group here, so you're kind of backwards because we want this to be normal in there, not like the finite group to be normal, but we can kind of move things around and be okay. Just from getting, another Mori fiber space of vibration too. Not just this one, another one. And then you swap things. And so, the only case where something crazy can happen is when you have those groups. And when you have those groups, it's going to be like here you have A, that's a generator coming from here. Here you're going to have your BAC that come from there. And then if you work out the presentation, you're going to see that, this A generates a normal group. So when you conjugate it with a B or a C, you get to A or A minus 1. And you see basically what's possible, and it turns out the only possible presentation is this HK that we had before. And to realize it geometrically, this is exactly going to be the case, where x is like this, above an elliptic curve, and the divisor is just the sum of two sections, both with coefficient 1, corresponding to the two quotients. And so, it's like asking of the fundamental group of this minus the two sections. So it's like it's a C-star bundle over an elliptic curve. You're attracted to an S1 bundle, so you have an S1 bundle over S1 times S1. And then it's oriented, so it's like principal, and you can even, write down like patching conditions and figure out the fundamental group really by hand. And so that's exactly this HK you got. So basically, this was a very fast explanation of why the modifiable space case should work. And then you have this one, and you would think, now it's Fano, we're very happy, it's the easy case, but actually it's the hardest one. And the reason for that is, x0 is Fano, but if you take x0 and delta 0, you're still Calabi-Yau, you don't have positivity. And so you don't know what to do. And so basically this case is going to split into more cases. So basically there's going to be a case of you already have standard coefficients. And then, if you already have standard coefficients, then if you were KLT, then this would apply already, the effective Campana-Claudon. And then the problem is if you have standard coefficients and you're not KLT. But then the good thing is, if you already have standard coefficients, then they're all of some nice form. So you can take some index 1 cover and then work with it. So this case, it's not easy, but it's 1 or 2 pages. So just believe me, and it's some work and it's okay. But you're still going to use basically Campana-Claudon and also blowing up, doing more MMPs to reduce down there. And also some Miyanishi Zhang results about resulting to, having some sections in an anti-canonical of a Fano, making sure your Fano is Gorenstein, then Gorenstein Fano of Picard number 1. They're more or less classified, and we know stuff about their anti-canonical system, so we can do more explicit things to figure it out. And then basically the problem is, okay, now if this is not standard coefficient, then you're very happy because the standardization will be smaller. So if you standardize, you remove a little bit. So now you're Fano. Now you have a Fano pair. So so this case says you start off with a genuine LC Fano pair, but now it's LC. So what you're going to do is just take a DLT modification again, but now instead of a KX MMP, run a KX plus delta 0 MMP, delta 0 standard, so like the Fano one. And now you do it again. And the good thing is now you stay DLT, so you wind up at the end with a new pair, and now it's DLT. And you could be in this case, but now you'd have a delta 0. So, that's, in this case, it's like you really use effective Campana-Claudon. If you wind up with a modifiable space, you use this, theorem again. And if you wind up with a Fano, well, you're back to beginnings, but now your pair is DLT, so it's much better. And so now, for the DLT pair, basically the next question is going to be, what makes it not KLT is having coefficient 1 things in it. So, this is measured by something called corregularity, but doesn't matter. So basically, if you have no component of coefficient 1, and your new delta 0 after your new MMP, then you just use effective Campana-Claudon, because DLT no coefficient 1 is just KLT. So that's good. If you have, at least 2 components of coefficient 1 that intersect each other, so quite a few of them, then you have results telling you that you have a 1 complement or a 2 complement to your pair, which means that basically you started with your delta 0, you could increase it a little bit by something effective a little bigger, and genuinely get a section of your kx0 or of 2 kx0 worst case scenario. So you get a 1 or 2 complement. And the thing is, when you increase coefficients, you might change the fundamental group, but as long as you have some divisibility going on, you still have a surjection. And the thing is, when you get to 1 or 2 complement, your coefficients are going to be, 0, 1/2, or 1. And if you take 0, 1/2, or 1, the numbers that correspond, and they're like, if you write them as 1 minus 1 over n, are going to be, the indices are going to be 1, 2, and infinity, and of these you have the usual order and the divisibility order, and they're the same order. So somehow, when you increase, in the usual order over R, it's the same as increasing divisibility-wise. So you get a genuine surjection. And if you started getting, 3 complements or 6 complements, it wouldn't be true anymore. Because, if you have a 4/5 coefficient in front of a component, and you increase it to 5, 6, then you had a 5 torsion loop, and you make it 6 torsions. So those groups have nothing to do with one another. So here it's really special that it's 1 or 2. And then the last thing is, what if you have exactly, okay, so it's not exactly 1, but basically, if you have one component of coefficient 1, so let me cheat a little, you could have several, but they don't intersect, but that doesn't happen too much. You could have 2 that don't intersect, but never more. But let me cheat and just say, what if you have just one component of coefficient 1? Then you're very happy because your Fano pair is now a PLT Fano. And it's like a little upgrade from DLT. It's like, DLT, we said it's always KLT or like normal crossings. PLT is like, you're always KLT, except if you have some coefficient 1s, but they're not going to be intersecting with other coefficient 1s. So they might intersect with some smaller coefficient. So it's a little better than, DLT. And from there on, so you have this PLT Fano of Braun number 1. Well, it's not done yet, because basically what do you do next? Well, you still have to do a lot of things, but basically the idea is going to be to make yourself look like you're walking with a toric pair in most cases. And in the other cases, since you have, so your pair is going to be X, something of coefficient 1, and then something with coefficient smaller than 1. And so you can also do adjunction with respect to S. And for PLT Fano pairs, you have a very cool thing where if you perform actual adjunction, you're going to get a pair that now is supported on a curve, kind of like we had with our Mori fiber space. And then this pair, it's going to be also like a Calabi-Yau pair, but maybe with no standard coefficients. And now you can, maybe for this pair, you find a complement. And the good thing is for PLT Fano pairs, if you have a complement here, it lifts to a complement of this pair. And so you replace this pair by somehow a better one. And now with this better one, it's very rigid what kind of pairs you can get. Most of them are going to be toric from some toric results by also Roberto, Moraga, other people, so McCarran, Braun, and other people. But mostly they're going to be toric places, and then you're going to have some very explicit other ones that all kind of relate with some Hertzogler surface, or you can get some other fibrations. And you just reduce to finitely many cases and describe the geometry. And I should stop.